So now we have a Mayer's formula that goes like this. Mayer's formula is Cp minus Cv equals to R. Cp minus Cv equals to R. This is called as Mayer's formula. Alright. Now we will be using for calculation of Cp or Cv values. Just remember, for monoatomic gas Cv is 3 by 2R, for diatomic it is 5 by 2R, and for triatomic or polyatomic it is 3R. Alright. Now if you want to calculate Cp, from here you know Cp equals to, if we take this minus Cv this side, so this will be R plus Cv. Alright. So if for monoatomic gas Cv is 3 by 2R, so add this with R, you get 5 by 2R. Similarly, if you have to calculate Cp for diatomic gas, what you will do? R plus Cv for diatomic, that is 5 by 2R. So you will get 7 by 2R. For polyatomic or triatomic gas, Cp equals to R plus 3R. So that will be 4R. Alright. So this way you can calculate Cp or Cv. Cv you have to remember, and Cp you can calculate automatically. Now we have Poisson's ratio gamma. Poisson's ratio gamma equals to Cp by Cv. Cp by Cv. Gamma is called as Poisson's ratio. This is equals to Cp by Cv, right? So for each gas, type of gas, let's say if it is a monoatomic gas, you can calculate Cp by Cv accordingly. If it is a diatomic, it is a triatomic, you can calculate Cp by Cv values. For example, Cp by Cv for a monoatomic gas comes out to be 1.66, for a diatomic it comes out to be 1.44, and for triatomic or polyatomic it is 1.33. We will be using this in numericals, right? Now we are talking about expansion of ideal gas. So expansion of ideal gas shows that if in an isothermal expansion delta U equals to 0. So according to the first law of thermodynamics, delta U is equals to Q plus W. For isothermal, delta U has a formula, NCV delta T. So isothermal process, this delta T equals to 0. For isothermal process, delta T equals to 0. So this comes out to be 0. So for isothermal, if it is 0, so what will be the relation between Q and W? Q comes out to be minus of W. Alright. So the signs we can use for calculation purposes. So Q equals to minus of W. From here you get exact relation. Similarly, if work done is in isothermal process, so for expansion, work done in reversible process comes out to be minus 2.303 RT log of B2 by B1. If it is in terms of pressure, you have formula 2.303 RT log of P1 by P2. So these are expansion formulas, isothermal expansion in a reversible process. Similarly, if you want to calculate formula for compression, what you can do is, in compression just reverse this. This will be V1 by V2 and this will be P2 by P1 for compression. Alright. So these are few formulas which you will be needing for calculation. Now next topic we need to discuss is free expansion. So what is free expansion? As the name suggests, free means there is no external pressure. That means external pressure is 0. That means expansion against vacuum. When there is no pressure outside, then the expansion is happening against vacuum. So expansion against vacuum is known as free expansion. So the formula, as you know, work done has a formula P external into delta V. So when P external equals to 0, so work done also equals to 0. So in case of free expansion, work done equals to 0, right? Next, adiabatic expansion. Adiabatic expansion, as you know, heat transfer in adiabatic expansion is 0, Q equals to 0. So from first law, which is delta U equals to Q plus W, we will put Q equals to 0, we get change in internal energy equals to work done, right? So if gas is doing certain work, it is using its internal energy. For example, if expansion is happening, gas is expanding. So what do you think? If gas is expanding, there is no absorption or release of heat. So if gas is expanding, so in the expansion of gas, what kind of energy is used? It is using, gas is using its own energy. So if it is using its own energy, then its net energy will decrease. So net energy or internal energy decrease is shown by cooling. So during adiabatic expansion, cooling occurs. Similarly, if work is done on the system, compression, in compression or adiabatic compression, work is stored in the form of internal energy. So temperature increases. In adiabatic expansion, heating occurs. In adiabatic expansion, cooling occurs because there is no exchange of heat, right? So Q equals to 0. So whatever change in internal energy happens, that is equals to work done. So in adiabatic expansion, cooling occurs. In adiabatic compression, heating occurs. All right. So these are few things we were needing to be discussed here, and we have few more relations which you will be using for adiabatic numericals. And what are these? For a reversible process, T1 by T2 equals to V2 by V1 to the power gamma minus 1. Similarly, we have another formula which is T1 by T2 to the power gamma equals to P1 by P2 raised to the power gamma minus 1, which you can directly use for the calculation of adiabatic expansion problems. And work done same way you can calculate, which is from the formula which is given NCV delta T, right? Or nr by gamma minus nRT by gamma minus 1, nr delta T you have to put, because it is the change in happening in temperature. So nr delta T by gamma minus 1. And what is gamma? Gamma depends on gas, what kind of a gas we have taken. If it is monatomic gas, you will take 1.6666. If it is a diatomic, you will take 1.33. If it is a triatomic, you will take 1.33. All right, 1.4 for diatomic and 1.3 for triatomic. All right, so this is it.